Hello, Chemistry 30, and welcome to your lesson on KW. This is getting into acid and base chemistry. And what we're doing is we're continuing on with our whole idea of looking at chemical equilibriums, but we're realizing that acids and bases often have an equilibrium with water, especially if they're a weak acid or base, and even water itself has an equilibrium that's going on between hydronium and hydroxide that you're going to find out about, and that's what Kw is. It's the equilibrium constant for the expression of the equilibrium water has with itself to make hydronium and hydroxide. So we're going to get into it. First of all, we're going to do just a bit of review from Chemistry 20, talking about what we already understand for acids and bases, which, spoiler, it's going to change. But for now, you kind of have an understanding of what acids and bases are. So you right now are on the modified Arrhenius theory for acids. And modified Arrhenius theory, and I don't know if you can hear my kitten there, he's making a ruckus. He's upset for some reason, but I'll ignore him. Modified Arrhenius for acids basically says that when an acid is in water, it reacts with the water to make hydronium. So it's making hydronium ion by reacting with water. And we're going to go through some examples. Hydronium is H3O positive aqueous. So what's actually happening here is when I take a look at water, what the structure looks like is we end up having 3 hydrogen atoms attached to the oxygen, and then we still have a lone pair on that oxygen as well. So this would be a hydronium ion. So hydrogen ions don't actually exist by themselves in water, but instead it bonds 2 waters and makes this hydronium ion that has an overall charge of 1 positive. All right, so let's take a look at a few examples. Say goodbye to the kitten who's causing all sorts of trouble. He's leaving the room. Okay, so we're going to take a look at, for example, nitric acid, and these are both strong acids. So what happens is when we take an acid and put it into water, it's actually reacting with the water. So I have HNO3 aqueous plus H2O liquid, and that's going to make for us hydronium. So this hydrogen ends up going to the H2O and makes H3O positive aqueous. Then I'm also going to have nitrate ion, which is NO3 minus aqueous as well. So I have those 2 ions that are forming. In the same way, if I were doing this with HCl, so I have HCl aqueous plus water, it's going to react with the water in order to make, again, hydronium, H3O positive aqueous, as well as chloride ion, Cl minus aqueous. So it's going to make those 2 things. Now, when I talk about bases for the most part, what we're dealing with in the past was ionic hydroxides, right? So I have something that is ionic, so it has a metal with a hydroxide ion. And then essentially what happens is these bases end up just dissociating in the water in order to form the cation and the hydroxide ion. And that hydroxide ion is what makes a base, right? That's what gives base solutions basic properties. We also can have things that react with water to make hydroxide. So the other option of what happens is it reacts with water, reacts with H2O to make hydroxide. So we have 2 different processes here, right? We either have dissociation making hydroxide, which isn't a reaction. It's just the 2 ions that were already there in the ionic compound separating, and one of the ions happens to be hydroxide. And then we actually have a reaction where water reacts with something in order to make the hydroxide. So we have those 2 options, excuse me, that can occur. So for example, if I have LiOH aqueous, this can dissociate in order to make Li positive aqueous and hydroxide. How do I know it dissociates? Well, this is ionic, right? This is an ionic compound, so I know it's going to break into its 2 ions if it's soluble, which this is. Everything group 1, lithium is group 1, dissolves in water, so I know it's soluble. So it's going to dissociate into the two ions that make it up, mainly lithium ion and hydroxide ion. So this isn't a reaction, it's just a dissociation. Again, the ions that were already there in the ionic compound are just separating into its two parts, which happens when something dissolves in water. The action of the solvent separates the ions in the ionic compound to be now separate ions floating around in solution, which is what dissociation is. Now, ammonia, NH3 aqueous, this is not the same. Ammonia is not ionic, and instead what happens is this reacts with water plus H2O liquid in order to make NH4 positive aqueous and hydroxide, OH minus aqueous. Both of these things are what make these solutions a base, right? Hydroxide is what's responsible for making a solution basic. Now for this second one, if you're like, I don't know how we figured that out, don't worry about it. We're going to, in a future lesson, talk about how we can predict whether a solution will be acidic or basic and figure out what's going on. For right now, we're just looking at this and explaining that bases can be made in two different ways, either by dissociation or by a reaction with water to make hydroxide. When we talked about acids were always reactions with water to make hydronium to make an acid. So that's our modified Arrhenius theory. Now, let's get into the water side of things. Water actually reacts with itself very, very weakly in order to make a hydronium and a hydroxide. This is called the self-ionization of water. So, 2 out of every billion water molecules meet up, and essentially what they do is that 2 out of every billion water molecules, 1 hydrogen leaves 1 water. Let's do it this way. 1 hydrogen leaves 1 water and ends up going to another water. So water actually just essentially reacts with itself, making a hydronium ion and a hydroxide ion. Now, could these again react to make waters? Yeah, but as soon as that happens, because it's equilibrium, this forward reaction will happen again. So water always has this equilibrium taking place where 2 out of every billion waters is making a hydronium or a hydroxide. Okay, so we have the forward reaction and the reverse reaction happening at equal rates, but our amount of hydronium and hydroxide is remaining constant. And this is working ahead a little bit, but the concentration of both of these things will be 1 times 10 to the negative 7 moles per liter. Maybe that's somewhat familiar, this value, for good reason. Okay, so both of these concentrations will be 1 times 10 to the negative 7 moles per liter. Now again, this is an equilibrium. So I'm constantly making hydronium and hydroxide ions, and hydronium and hydroxide ions are constantly reacting to make the waters again, right? So we have an equilibrium happening where forward and reverse reactions are happening at the same rate. But as a result, concentrations are remaining constant because again, it's a dynamic equilibrium. So this is called the self-ionization of water. It's called that because I'm making ions by reacting with itself. And as a result, water, even distilled water, does conduct very, very, very weakly because it has these ions present. Okay, again, weak conduction, barely conductive, but it is conductive a little bit, even distilled water, because I do have some ions around, and that's what I need in order for electricity to actually move through solution, is I need charged particles, ions, to be present. All right, so let's analyze this particular equilibrium and figure out what the equilibrium expression and constant would be. So I have products and I have reactants. So knowing what you know about equilibriums, how would this look? Well, it would look like this. I have H3O positive aqueous on top because that's a product, has a coefficient of 1, so no coefficients or no exponent here. Then I have hydroxide OH minus aqueous. And then these waters are liquids. And you might think, well, I have more than one liquid, but it's the same thing. Really, this should be just written as 2 H2O liquids, right? So as a result, I don't have anything at all in the denominator. So my Kw is equal to hydronium concentration multiplied by hydroxide concentration. And this is equal to 1.0 times 10 to the negative 14. This is the water ionization constant, the Kw value. You have it in your data booklet. You don't have to memorize it. You've got it. And the reason why is if we went back to this for distilled water, right, we actually could work that out, that if it's 1 times 10 to the negative 7, 1 times 10 to the negative 7, I multiply those two values together, that's going to give me 1 times 10 to the negative 14. Based on this value, is it product or reactant favored? Oh my goodness, is this ever reactant favored? Because this value is super tiny. 1 times 10 to the negative 4, that's almost 0, right? It barely happens. When you think about that, that's 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 1. Yeah? That's that small for a constant. So most of it stays as water, a teeny tiny amount, again, 2 molecules out of a billion water molecules end up doing this. All right, so value for hydronium and hydroxide, we already talked about this for distilled water. In distilled water, hydronium concentration will be equal to hydroxide concentration, which will be equal to 1.0 times 10 to the negative 7. What do you think is the significance of this 7? And the answer is, you probably realize that that equals the pH or the pOH of neutral stuff, such as distilled water, which is kind of interesting. So we're going to go back into pH and pOH later on and calculating that. But that's why that 7 is familiar, is because of pH and pOH and talking about it in Chem 20. All right, so using Kw, I can now use this expression of Kw is equal to hydronium multiplied by hydroxide. And I can figure stuff out using this. So for example, if I have hydronium concentration, and it doesn't have to be 1.0 times 10 to the negative 7, we can shift it and then figure out, because it's equilibrium, what is the hydroxide concentration, and Kw, the constant, will always stay the same. We're always keeping it the same temperature. We're always assuming 25 degrees Celsius. So if I have a hydronium concentration, I can use that using Kw to find a hydroxide concentration. And the formula for that then would be hydroxide is equal to Kw divided by hydronium. In the same way, if I happen to have a hydroxide concentration, well, then I can find hydronium, H3O positive, by saying that's equal to Kw divided by, of course, hydroxide. Now, in my work, because this is still an equilibrium expression, I don't show units. I leave them out. I don't have units for Kw. I leave those out. So whenever I'm within an equilibrium expression, I am unitless. I am just writing the numbers, working it out, and getting an answer. And then once I have an answer, that's when I put the units on there, because that's when I know. All right, so let's now talk about the balance between both ions when I have acidic, basic, and neutral solutions. So when I have an acid, what do you think is going to be larger? The hydronium concentration or the hydroxide concentration? And the answer is the hydronium is going to be a larger number than the hydroxide, which is what makes it acidic, that I have more hydronium present than I have hydroxide. Now I can also say that in this case, hydronium concentration will be greater than 1.0 times 10 to the negative 7 moles per liter, right? While my hydroxide, OH minus, must be less than 1.0 times 10 to the negative 7 moles per liter in that case. But if I multiply both of these concentrations together, it will still get Kw. It will still give me 1.0 times 10 to the negative 14. For a base, hydroxide will be greater than hydronium, H3O positive. So I'm going to have hydroxide greater than 1.0 times 10 to the negative 7 moles per liter. This probably feels slightly silly going through it at this point after just doing the last one, but oh well. Hydronium will be 1.0 less than, 1.0 times 10 to the negative 7 moles per liter. So that will be the balance for a base. Now for neutral, we already talked about this. At neutral, hydronium is equal to hydroxide concentration, which will be 1.0 times 10 to the negative 7 moles per liter. Just a quick note, people often get confused about these negative exponent concentrations. So you have to remember that when I'm getting larger as a value, then this exponent is going to get smaller in number, greater because it's negative. So like -5, -4, -3, right? That means that the concentration is increasing because I'm getting closer and closer to 1. Okay, now if this gets larger or more negative down here, I know words, then that means it's getting less. It's a lower concentration. So just realizing how negative exponents work is critical in this and understanding that, because that can be confusing. Some of you maybe not so good with the exponents. So yeah, just kind of remember the nature of negative exponents, that as the exponent is getting larger as a negative, it's getting smaller. And as it's getting smaller as a negative, it's actually getting then larger. All right, so we're going to do a quick example here. I got to get a calculator ready. And the calculator is here. All right, so let's try this out. So information I have from this is I have a hydroxide ion concentration of 2.50 moles per liter, and I want to find the hydronium. So I know that Kw is equal to hydronium multiplied by hydroxide, which I know Kw is equal to 1.0 times 10 to the negative 14. So I've got my hydroxide ion concentration of 2.50 moles per liter. So now if I divide both sides by hydronium, H3O positive, of course, divide, H3O positive, then I have, oh, nope, sorry. So I'm going to back it up and not make a massive mistake here. I'm dividing by hydroxide because that's a concentration I know, and I'm trying to find hydronium. Oh, that would have been bad. All right, so I've got hydronium is equal to Kw divided by that hydroxide concentration that I have, which is a 2.50 moles per liter. So I have 1.0 times 10 to the negative 14, and I'm dividing that by 2.50. Now again, I'm going to leave the units out of my equilibrium expression. I don't want it in there because I never write units in an equilibrium expression. So now let's go to my calculator and plug this in, and let's talk about the E, the exponent button, because that is critical in this chapter. I'm going to press second and then go to this comma, which has the EE there. That does my exponent kind of function. So what that is E is the same as writing times 10 to the power of, but it's all good for order of operations and stuff. So essentially it treats it still as one number, not as a operation between two numbers with the E. So it treats it all as one number and makes it really easy in terms of plugging things in. So I have 1.0, second E, negative 14, and I'm going to divide that by 2.50, and I end up with an answer of 4 times 10 to the negative 15. So I have an answer of 4.0 times 10 to the negative 15. And now I put the unit on, because I'm out of my equilibrium expression, of moles per liter. So that would be my final answer for my hydronium concentration, my H3O positive. What we're going to do later on is work with this and then find things like pH and POH, but that's a different lesson entirely. 4.0 times 10 to the negative 15 moles per liter. Next example, you could try this one out in your workbook, but first let's quickly talk about one problem here that you have to realize. In a 0.15 mole per liter solution of hydrochloric acid at 25 degrees Celsius, what is the concentration of hydroxide ions? There is just kind of a step that we have to take first, which is realizing that if I'm taking hydrochloric acid, HCl aqueous, then that reacts with the water in solution in order to make for us quantitatively, so it's 100%, It's not that it happens like in equilibrium, but this is a full reaction to make hydronium and chloride ion. So if I have 0.15 moles per liter of HCl, then I'm going to have 0.15 moles per liter of hydronium because all of the HCl reacts with water in order to make hydronium. So just kind of an important thing to note before we go into this question. And now that you know that, why don't you try it out and see if you can figure out the concentration of the hydroxide ions using what you've learned about Kw. So we would start out by saying Kw is equal to hydronium multiplied by hydroxide. I'm trying to solve for hydroxide, so I'm going to divide this by OH minus. No, again, hydronium, because that's what I have. Oh, this is a day. I'm going to divide by hydronium on both sides in order to solve for hydroxide. So I'm going to end up with hydroxide OH minus is equal to Kw divided by that hydronium, H3O positive. So I have 1.0 times 10 to the negative 14 divided by my concentration of hydronium of 0.15. Again, I'm going to leave units out of it for this work because I'm in an equilibrium expression. So 1 second E negative 14, because that is my Kw value, divided by 0.15 gets me a value of 6.666666 forever. So we're going to put down 6.7 times 10 to the negative 14 moles per liter. So this is a very acidic solution, yes, because I have an incredibly low hydroxide concentration. But this is interesting. Even like strong acids, there's still some hydroxide present in solution. Is it an incredibly small amount? Yes, there is. It's very tiny, very low concentration, almost zero, but it's still there. Okay, so I still have, even in the strongest acids, a little bit of hydroxide because I still always have present the equilibrium of two waters reacting together, self-ionizing in order to make hydronium and hydroxide. This equilibrium is present in any solution that contains water. Okay, so I can use that equilibrium to figure out hydronium or hydroxide if I'm given the other, for the Kw being 1 times 10 to the negative 14. All right, so that's it. That's your examples. Try out the Kw worksheet and see how it goes.